Hello everyone! In this video we're going to go over lines in space. So as we jump into this, we're going to go over how exactly to create that line or make it some sort of equation. So let's recall a few example videos ago we talked about parametric equations for a line in R2. So R2 is that two-dimensional line, and the parametric equation we had x as some function of t, and we also had y as some function of t. And for a line, as opposed to a line segment, t went from negative infinity to infinity for that line. So for a parametric equation of a line in R3, so that's in 3 dimensions, if we're passing through the point P x naught, y naught, z naught, well, if this was 2 dimensions, so if we didn't have that z naught, x would be equal to x naught plus a of t, right? And then y was equal to y naught plus b of t, where a and b were constants, and using those two we were able to create the slope of the two-dimensional line. But we can think of this a as that change in the x direction, the change in the y direction would be b, and now we have a z, right? Because we're in 3 dimensions. So x, y, and z, and this is going to be z naught, because we're passing through that point, plus some constant c of t. And that's for negative infinity is less than t, which is less than infinity. So these equations are the parametric equations of a line in 3 dimensions. And that's just one way to express a line. Let's talk about it though if we wanted to define a unique line L in vector form in R3. So we know how to do it in parametric form. Now we just got to figure out how to do it in vector form. So it says let L be the line passing through the point P of x naught, y naught, z naught, parallel to some non-zero vector v that goes in the direction a, b, c. So I've started out kind of showing this within a picture, within some graphic. Let's make this point P here. So P right there is x naught, y naught, and z naught. There's our point P. Now if we wanted to write a vector equation, remember, summing vectors, multiplying a scalar to a vector, that's going to result in a vector itself. So the way we're going to write L is it's going to be some equation of vectors. And let's envision line L as this green line here. So let's just define our origin as point O. So if I wanted to somehow write a vector equation for line L, I want to be able to find any point on that line. So let's just make this point over here, which also falls on that. Let's call this some point where we have x, y, and z. And let's go ahead and just call that point Q. So what I'm trying to figure out is this vector OQ, because that is some point, some undefined point, it's just some variable x, y, z that falls on that line L. So I'm going to try to figure out how I can write vector OQ, hence a vector equation. Now I know to get to that line, I'm going from O to my defined point P. So vector OP will get me to a point on that line. So vector OQ is going to be OP plus some other vector going from P to Q. But I don't exactly know what that vector is. However, I want it going in the same direction or the opposite direction because I'll just be able to multiply that by some scalar. And you can see that we have some non-zero vector v that is parallel to the line. So if we have some vector v that's parallel, once we get to that line L, all we need to do is multiply by a scalar to get to Q. So then I'm going to take my vector v and multiply it by some scalar. I don't know what that scalar is, so I'll just leave that as variable t. So you can see that if O to P brought me to this point here, which is my point P, that's vector OP, And then let's say that vector v went to about right here. Well, then I would need approximately 2v to get me to OQ. So then my t in that case would be 2. So I'll just draw this red vector from P to Q and I'll call it TV. So this is some vector v that's multiplied by a scalar t. So that's our vector equation of this line. And let's go ahead and break this up into components so we can see. So OQ is some vector, remember, head minus tail, where this O was the origin, so the point 0, 0, 0. So if I did O to Q, that would be x, comma y, comma z, because I'd have x minus 0, comma y minus 0, comma z minus 0. So you can see that this is some variable vector, meaning that my points x, y, and z aren't defined. However, my vector OP, if I defined x naught, y naught, z naught as specific numbers, that vector is going to be x naught, y naught, z naught, head minus tail. So this vector x naught, y naught, z naught, if I add that to t times some vector v, which we said v was the components a, b, c, then you can see I have my vector equation. So you can see that if I changed my point Q up and slid it down on my line L, then I would just have a different t, a different scalar that would be multiplied by my vector v. So this would be the only thing that changes depending on where my point is on my line. And that's what makes it a vector equation for that line. The only thing that's changing is that t variable, and that's giving me all the other points on my line. So the vector equation of some line L passing through point P of x naught, y naught, z naught in the direction of vector v is, well, using our OQ, vector OQ equaling vector OP plus TV, then we could write that as x, y, z, that vector x, y, z is equal to the vector x naught, y naught, z naught, which if you think about it gives us, head minus tail, that's that point x naught, y naught, z naught, but as a vector, so that we have magnitude and direction. Then we're going to add that to some scalar t multiplied by vector a, b, c, which is vector v, which we have defined as some vector parallel to our line L. So in the direction of L. And in this case, because it's a line, we're going from negative infinity is less than t, which is less than infinity. So essentially, t is any real number. Now I just want to look at this and then think about that parametric equation above. Let's go ahead and combine these vectors over here through vector addition. So if I had x, comma, y, comma, z equal to, if I multiplied this t in, I'd have t times a, comma, t times b, comma, t times c. Now think about adding that vector with the scalar already multiplied in to the vector x naught, y naught, z naught. Well, then I'd have x naught plus at, y naught plus bt, and z naught plus ct. Look at these individual components, x, y, and z. Those are my individual parametric equations for the line. This is x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. And that's for t going from negative infinity to positive infinity. So you can see that vector equation and that parametric equation are fairly similar. The vector equation just has the parametric equations as those individual components. So writing or shifting between each of those two equations or each of those two forms should be fairly intuitive. So let's go ahead and try that with example 1. So in example 1, it says find a vector equation of the line L that passes through the point 3, 5, 2 in the direction of v as 1, negative 4, 2. So we're going to find that vector equation first, and then we're going to find the corresponding parametric equation. So remember that vector equation, we're going to have sum x, y, z, that vector, is going to be equal to the vector that's created from our given point and the origin. So head minus tail, that's going to be point P minus our origin. Again, let's just call that point O of 0, 0, 0. Which, remember, it's a vector, so keep thinking that it's always going to be that head minus tail, but we can just take those individual coordinates and put them as vectors. 3, 5, 2. So I just want to reiterate the fact that this is not a point, it's actually the vector. So it has direction and magnitude. And if we put the tail of this vector at the origin, we'd be at the point P. So we're going to take that and add that to some scalar t, which I'll define t over here as being from negative infinity to infinity, because indeed we are doing a line, not a line segment, and the line continues on in both directions. And it says that vector v is 1, negative 4, 2. And there we have it. That's our vector equation. So if we wanted to write this as parametric equation, all we really need to do is find the individual components of that vector once we multiply the scalar in and then combine those two vectors. So you can see that that x component is going to be 3 plus t times 1, which is 1t, so 3 plus t. Y is going to be 5 plus negative 4 times t. So I'll write that as 5 minus 4t, and then z is going to be 2 plus 2t. And again, that's from negative infinity is less than t, which is less than infinity. So there we have it as a vector equation and as parametric equations. Now let's move on to example 2. In example 2, we're going to find the vector equation and parametric equations of a line L that passes through the points P of 1, negative 2, 1 and Q of 4, 3, 5. So unlike above, we don't have the direction V, but we know that if the line passes through point P and it also passes through point Q, that vector P to Q is going to give us the direction that that line's heading. So we just need to calculate vector PQ, and that's going to be equivalent to our direction vector V. So remember, head minus tail, the coordinates of Q minus those coordinates of P. So we'll have 4 minus 1, comma, 3 minus a negative 2, and then 5 minus 1. So this vector PQ, which is technically going to be our vector V, is going to be 3, 5, 4. So now that I have my direction V, I just need to use my point P to create that vector OP, so from the origin to P. So I have my vector x, y, z. That's going to be equal to the vector 1, negative 2, 1, plus some scalar t multiplied by v, which we calculated to be 3, 5, 4. And again, that's from negative infinity is less than t, which is less than infinity. And there we have it. There's our vector equation that passes through both points P and Q. All I needed to do was find the direction of that. I could have also used point Q as my vector going from O to Q. So if I did x, y, z as 4, 3, 5 plus t of 3, 5, 4 from negative infinity to infinity, those represent the same exact line. I know it doesn't quite look like it, but let's think about this logically, right? Because if we started at 1, negative 2, 1 versus vector 4, 3, 5, think about this. If I set t In the second equation, if I made t equal to 0, then we would have 4, 3, 5. Whereas up here, if I set t equal to 1, 1 times 3, 1 times 5, 1 times 4, adding those two vectors together, I would get vector 4, 3, 5, which is the same as this down here. Or vice versa, I could make t, as opposed to 1 up here, I can make t 0, so I have the vector 1, negative 2, 1, and then here, as opposed to making t 0, I can make it a negative 1, to where I have 4 minus 3, which gives me 1, 3 minus 5, which gives me a negative 2, and 5 minus 4, which gives me a positive 1. So I have that same vector here. So you can see, depending on what those t values are, I'll be at different points along that line, but it's still the same line. So either way of writing this equation is perfectly fine. Now let's go ahead and write this as a parametric equation, and I'll go ahead and just use my first one. So that would be x equaling 1 plus 3t, and then I have y equaling negative 2 plus 5t, and then I have z equaling 1 plus 4t. And again, that's from negative infinity is less than t, which is less than infinity. So continuing on, we're going to talk about the intersection of lines in space. So let's think about intersection of lines in 2 dimensions. Well, those lines are going to intersect at a point, right? Unless those lines are parallel. Then you can see they will never intersect. It's kind of the same concept in 3 dimensions, except now if you think about a line in 3 space, or R3, then when I have 2 lines, they don't necessarily have to fall in that same plane and intersect. So I can have some line over here and some line over here that will never intersect because they're skewed. Or I could have it to where the lines will intersect, or I could have the lines be parallel and also never intersect. Or they could be parallel and intersect at all points, essentially making them the same exact line. So what we're going to do in this example, we're going to figure out if the lines L1 and L2 are parallel, if they intersect at a single point, or if they're skew. And again, intersecting at a single point is exactly how it's defined. Those 2 lines do intersect in 3 dimensions, and they intersect at that one point. Skew is where they don't intersect, but they're not parallel. And again, if they're parallel, as long as they're not the same line, they will never intersect. And for example 3, if they do intersect, we'll do a little bit of extra work and find that point they intersect at. So if we have L1 as x equals 1 plus 6t, y 3 minus 7t, and z equals 2 plus t, that is L1. So that is the parametric description of that line. And L2, we have another parametric description of the line. We're just changing up that variable a bit, so that variable is now going to be s. So we have 10 plus 3s, y equals 6 plus s, and z equals 14 plus s. So remember, if 2 lines are parallel, they're going to be heading that same direction. They're going to have their a, b's, and c's for that vector v, that direction vector, be scalar multiples of each other. So if we just look at what's multiplied by t in each of our equations, or in the case of L2, what's multiplied by s, if these are parallel, I will be able to multiply my coefficients, so 6, negative 7, and 1, I would be able to multiply those by some scalar to get 3, 1, and 4, the direction of my vector v in the case of line 2. So 6, I would need to divide by 2 to get 3, but right away, negative 7 divided by 2 does not give me 1. So I know right off the bat, these are not parallel because that vector v in each of them are not scalar multiples. So right away, I can eliminate the fact that these are parallel. And if they aren't parallel, they also aren't ever going to wind up being the same line. So I know that they will either intersect at one point or they're going to be skew and not intersect at all. Now, how exactly do we figure out where they intersect? Well, that's going to be us setting up a system of equations, because if they intersect at a point, the x coordinates will be the same, the y coordinates of each line will be the same, and the z coordinates of each line will be the same at that point. And I have x defined for each, y defined for each line, and z defined for each line. So again, using that system of equations, I'm going to look at x first. So I want to see when 1 plus 6t, x for line L1, is going to equal 10 plus 3s. That's my x for line 2. Now I have two variables, but I can solve for one of them and then use the fact that y is 3 minus 7t equals 6 plus s, my y for line 1 and my y for line 2. I now have two unknown variables, but I have two equations, so I'll be able to set up this system of equations. So what I'm going to do is I'm going to solve for, let's solve for s in this first equation. So I'll subtract 10 from both sides to get that negative 9 plus 6t equals 3s. And then I'll divide by 3. So I'll get negative 3 plus 2t is equal to s. So because I know what s is, I'm going to plug that in for s in my equations for y. So I'll get 3 minus 7t equals 6 plus negative 3 plus 2t. Because again, that's what s is equal to. So simplifying this down, 3 minus 7t equals 6 minus 3 is 3 plus 2t. So now you can see that if I subtracted 3 from both sides, I'd get that negative 7t is equal to 2t. And then if I added 7t to the other side, I'd get that 0 is equal to 9t. So in this case, t is equal to 0. So if t is equal to 0, then what is s? Well, if t equals 0, then negative 3 is going to be equal to s. So now I have defined t for this relationship and I've defined s. So let's see if using that s value and that t value gives me the same exact point. Because if it does, well then I know L1 and L2 will intersect at that point. So using t of 0 for L1, I'll get that x equals 1, y equals 3 minus 0, which is 3, and z equals 2 plus 0, which is 2. So I'll get the point 1, 3, 2 for L1. Now looking at L2, that's where I'm going to use that s equals negative 3. I'll get x equal 10 plus 3 times negative 3. Then I'll get y equal to 6 plus a negative 3. And z equals, let's slide this over just a tad, 14 plus 4s. So let me go ahead and slide that up so you can see 14 plus 4s, which remember, s is a negative 3. So let's do this math. That's going to give me that x is equal to 10 minus 9, which is 1. This is going to give me that y equals 6 minus 3, which is 3. And then 14 minus 12 is indeed going to be z equal to 2. So I get that same exact point, 1, 3, 2. So I know indeed they intersect at 1, 3, 2. Now, remember when we mentioned skew? All that would have had to happen was this equation, 14 plus 4s. What if I would have made this as opposed to 14 plus 4s? What if I would have made this a 10 plus 4s? And let me write this in a different color. If I would have made that 10 plus 4s, when I plugged in negative 3, I would have gotten 10 minus 12, which would have given me a negative 2, which would have given me the point 1, 3, negative 2, which is not the same as the point 1, 3, 2. Therefore, those would have been skew. So only one of those coordinates has to not be the same for them not to intersect. So again, the line did intersect at the point 1, 3, 2, but let's go ahead and jump into a little bit more practice just to help tie everything together. So in number 1, we're going to find the parametric and vector equations of the line through the point -2 to -1 in the direction of vector 4, 5, 1. So here we have it. X, Y, Z, I need some vector plus the scalar of my vector V, because V is that direction of our line. And that scalar is going to be the vector I get using the point and the origin. So -2, 2, and then -1. And this is for negative infinity is less than t, which is less than infinity. There we go. There's my vector equation, and I can use that to help me get my parametric equation, because x is going to be equal to -2 plus 4t. Then I have y is going to be equal to 2 plus 5t. And then I have z is going to be equal to -1 plus 1t, which is simply plus t. And again, that's for negative infinity is less than t, which is less than infinity. And lastly, in practice problem number 2, we're going to determine whether the lines are parallel, meaning they're going the same direction. So the v of R1 and the v of R2 would be scalar multiples, or they intersect at a single point, or they're skew, which means they don't intersect at a point, but they're not parallel. So if they intersect, just like in example 3 above, we're going to find that point of intersection. So now we're given our lines as vector equations as opposed to parametric equations, but the same concepts still apply. So remember, if they're parallel, that direction vector, so our vector v, is going to be a scalar multiple. And if we look at this, v in this case is 2, 3, 2, whereas v in this next case is 4, 6, 4. All I have to do is multiply this vector v by 2 to get 4, 6, 4. So these are indeed parallel. And with that, we wrap up our lines in space examples and practice worksheet. If you have any questions, please leave them in the comments below. And until next video, good luck with your online learning.